All right, everybody. Hello, and welcome to our next topic, which is hypothesis testing. And hypothesis testing is arguably the most important of all topics we will cover in this class. And why is that? It's because hypothesis testing is how we make conclusions about data. So we've been inching our way towards inferential statistics by doing descriptive statistics and probability. And now we're kind of going to combine all of those topics into one massive technique, which is hypothesis testing. So again, just tune in for this one. This is going to persist. These topics are going to persist for the remainder of the semester, for the remainder of our topics. So let's go ahead and get to it here. Here we are at our slides for hypothesis testing. All right, so let's start by, we've talked about hypotheses before, but let's remember what hypotheses are. All right, what is a hypothesis? Well, a hypothesis is a statement, all right, and they're statements that are intended to be tested, statements that often house a prediction, and we're going to talk about the different nature of predictions as we go here. But the beautiful thing about hypotheses is that we're always going to have two, and we're going to get to that here in a moment, but we're always going to have two hypotheses. Either something happened or it didn't, all right, very vaguely speaking. But here we have, again, a cute little cartoon to kind of summarize hypothesis testing. Hypotheses are meant to be very concise and very clearly illustrate what it is you might be trying to predict. So hypothesis testing as a procedure is systematic, and it's how we make conclusions about results from a research study. So this goes back all the way to our very first set, or our very first topic, which is that statistics are based on samples that are drawn from populations. So when we're doing a hypothesis test, what we're doing is we're taking some sample data and making some prediction back about the population. So this is a powerful thing, right? If we can't get all women to participate in a study, we can at least get a sample, have a prediction of how they're going to perform on a given measure, and then make an inference back to the entire population that we're interested in making a statement about. So I have a slide up next here, which is one of those procedural slides. So don't stress maybe writing this all down if you're taking notes, but let's just take a look. All right, so how do we put a hypothesis into action? Well, the first thing we need to do is state a hypothesis about a population. Maybe we have a prediction here about sexuality, all right, another big topic in psychology. Maybe we predict that out of all college seniors, 10% are virgins, all right? That's a prediction, it's clear. It's a statement about an entire population. We're likely not going to go ask everybody in this particular population, but we can say draw a sample, see what data comes from that, and then make a conclusion about what we think is true of the population. So that'd be our step one, is state our hypothesis. We use the hypothesis to predict the characteristics the sample should have. All right, so if we're predicting that 10% of all college seniors are virgins, 10% of our sample should be, right, if we're pulling a sample of college seniors. Then we obtain our sample, we ask them some questions that would help us to address the specific prediction. Then we compare our sample to the prediction that was made in the hypothesis. And then we either have support or a lack of support for our hypotheses. And again, we set this up in a pretty elegant way to where only one of two things can happen at the end of a hypothesis test. And the reason that one of two things can happen is because we anchor everything around what we call the null hypothesis, right? The null hypothesis, or as we'll abbreviate it to, the HO, okay, the H subscript 0. So here we have it. We have a null hypothesis or a null prediction. So it's the prediction that we're starting with, and we'll start to get an idea of how these really work. But the word null, we've maybe heard this term before, null, N-U-L-L. It basically means void, right, or absent of anything. So the null hypothesis is always predicting the lack of a difference, the lack of an effect of anything that we're studying. And I think this becomes a lot more clear once we put examples to this. We'll practice writing null hypotheses today. Then the research hypothesis is the exciting one, or we're going to call this the alternative hypothesis, H subscript A, so the ha. So we have the ho and the ha, or the ho-ha, right? A fun little term to help us remember what we do first in a hypothesis test. The first thing is to set up our null and alternative hypotheses. So the alternative is what you're testing, something different than what's already known or assumed. So let's take another look here. All right, so we always have both of these. We always have two hypotheses, and this might seem a little bit strange, but we can think of the null hypothesis as something like a baseline. The null hypothesis is if nothing changes, there's no relationships made. It's just kind of our baseline, right? It's when nothing really happens. So maybe we have a prediction, right, that we have 10% of our college seniors being virgins. That could be our alternative hypothesis. The null would be no difference, right, or no change or nothing distinct about that group compared to other groups. Then the alternative hypothesis goes, ooh, right? Ooh, we see a change, we see a relationship. And hypotheses are all based on, or hypothesis testing is all based on probability or the likelihood that something will have occurred. So let's take a look at the four main steps for a hypothesis test. Here we have them. So 4 steps, and 4 steps that are going to follow us for the remainder of the class, all right? So a lot of what we're talking about here is going to persist through the rest of the class, because when we learn new statistics, we're going to want to set them up as a hypothesis test. So here are our 4 steps. We want to state our hypotheses, so you'll have to write out a null and alternative hypothesis for a given question. Then we set criteria for a decision, okay? So we'll elaborate on this in a minute, but this is based on probability. So if we're making a comparison of 2 things, what's the probability that they're going to, say, be the same or be different? So we will get to that shortly here. And then we're going to compute a sample statistic. So what we're going to do today is not much unlike what we've already been doing with z-scores, except we're using an entire sample instead of a single score when we do our calculation for z. And then the last thing we want to do is make a decision, right? We want to make a decision, and the decision revolves around the null hypothesis. We can either retain the null hypothesis, we can say, hey, this seems to be true, we didn't find any evidence that this is not true, or we can reject the null hypothesis and say, hey, the null hypothesis does not seem to be true, the alternative hypothesis seems to be true. So again, only one of 2 things can happen, which helps to simplify our decision making, because our data can be complicated, but we can boil it down to a few simple techniques like comparing probability or likelihood of occurrences to make a decision about the data. All right, so we're going to go through a few more general ideas about hypothesis testing before we put it into action. So the next major component here is what we call an alpha level. An alpha level, or a level of significance. Really important here is this is a probability, all right? So an alpha level or a level of significance is a probability value. So probability, just like we learn to calculate, right? So probability or chance or likelihood of something happening. So what we're going to be doing is setting a certain criteria, a certain unlikeliness that something's going to happen if our null hypothesis is true, right? So how unlikely something is to happen if our null hypothesis is true. That's what we're talking about here. And we create what we call a critical region on the normal curve. So we'll go ahead and draw this out in a moment here. But we have a critical region, and if our calculated statistic falls into that critical region, if the null is true, that's very unlikely to happen. So if it does, we would go ahead and reject that null hypothesis. Okay, so again, this sounds a little complicated. There are a lot of moving parts here, but I think you'll see that this is very procedural. There's just a consistent logic kind of strewn throughout the rest of the types of problems that we'll be hoping to do in this class. So the nice thing about alpha levels is we use consistent types of alpha levels across statistics. In fact, the most common one is 0.05, and then followed by that we have 0.01. And remember, these are probabilities. We can turn these into percentages. So an alpha of 0.05 means 5%. An alpha of 0.01 means 1%. And then I also have an alpha of 0.001 here, so that's less than 1%, right? And then we have the Greek letter alpha that we'll use to indicate our alpha level. So we can have a more conservative alpha level, all right? So 0.05 is the least conservative, 0.001 is the most conservative in this case, and we're reducing the likelihood, or increasing the unlikeliness, if you may, of something occurring. And I'm speaking in kind of vagueness here because that something can be a number of things. So we'll go ahead and hop into an example of one after we talk about one more thing, followed by a meme here. This is something we might be able to look back on and have a laugh about. But when we're talking about p-values or probabilities, if you want your conclusion to be convincing, we want it to be at a very conservative p-value. Because probability persists whether we want it to or not. Even things that are very unlikely to happen can still happen. All right, so say you find an effect of a drug at an alpha level of 0.05. All right, well, that's great, but there's still a 5% chance that you found that effect just due to randomness or due to a random effect. So again, we'll kind of comment back or loop back around to this. But if we find an effect, the lower the p-value, the more likely it seems to be a true effect. And we'll talk about errors and hypothesis testing here shortly. But I think the best way to think about this is, right, think of a lottery, all right? The likelihood of you winning the lottery is 0.00000, right? Lots of zeros before we get to an actual value. Even though it's incredibly unlikely, it can still happen, almost against all odds, right? Those are really poor odds, but it can happen, all right? So we're just going to keep that in mind and what we know about probability as we move into testing different research scenarios. So let's talk a little bit about those critical regions again. So alpha values like these, 0.05, 0.01, 0.001, in our class and for calculations we'll only be using values of 0.05 and 0.01. They determine our critical regions under a normal curve. So we're still hanging out with our friend, the normal curve. All right, because the normal curve justifies or explains where we expect data to be if it's normally distributed. So we're looking for the less likely scores to occur. Remember our 34, 14, and 2% rules on either side of the mean of a normal curve. So when we set up a critical region, we're only looking for the most extreme scores. And what we're ultimately doing is comparing a sample to something else. In this case, we'll be comparing a sample to a population. So we want to see if our sample fits into the distribution of the population or not. And if it doesn't, our null hypothesis is not true. So we mark these using critical regions. Critical regions are determined by probability or the likelihood that something is going to occur. So in addition to this, our critical regions are determined by the specific type of prediction we are trying to make. All right, maybe we're trying to make a prediction that we're just going to detect a difference between something, okay? Let's say that we think sleep affects mood, okay? When we make a statement like that, we're not saying that we think more sleep leads to a more positive mood. We're just saying that we think there's a relationship between sleep and mood, right? Maybe the more somebody sleeps, the grumpier they get, right? And we know that sleep is very important to things like mood disorders, like depression. So maybe we say sleep affects mood, okay? That's our hypothesis. That hypothesis isn't going in a specific direction, right? We're not saying that it's going to be greater or less than whatever our baseline might be. So that would be a two-tailed test. And again, we'll get to plenty of examples where we use these here. Differently, we might be, say, trying out a new medication that treats, let's say, what should we use? Let's go with anxiety, right? And we think that this specific medication is going to increase overall well-being. Well, that's a directional test because we're looking for an increase or a change from our null hypothesis. So just a few terms I want us to have heard before I start to use them in an example. So we're going to have critical regions or a critical region in either two tails or one tail, and that depends on what the question is asking, what our hypothesis is asking. Are we looking for an increase, a decrease, or just a difference from our sample to the population? All right, and then just a reminder that one of two things can happen, and only one of two things can happen. And those two things are either rejecting the null hypothesis and having some support for the alternative hypothesis, and the other is retaining the null hypothesis and not having any support for that alternative prediction that was made. So these are the only two things that can happen, and it's quite simple. If our sample statistic falls in the critical region on our curve, then we reject the null. If it doesn't, it seems that that data is close enough to what was true if the null was assumed to be true that just nothing really happens, right? We just continue to believe the null is true, we retain the null. Or some other language that you hear around this is failing to reject the null. Because when you come in with a research hypothesis or an alternative hypothesis, you're trying to support it, right? Or you're hoping to support it. That's why you made the prediction in the first place, because you think it's true. So that's why that fail to reject language is here. But again, one of two things can happen. We're retaining the null or we're rejecting the null. Okay, that's how I like to think about it. Just one of two things. And we're going to determine if our differences are statistically significant, all right? And this is a very important concept for all of statistics and all of science, all right? Statistical significance is something I've been mentioning all along here. It means that our result was very unlikely to occur if our null hypothesis was true. All right, the result is sufficient to reject the null hypothesis. So if we find a sample statistic that is in one of our critical regions, we reject the null, and we have what we call a statistically significant finding. All right, and then I have an example of wording here. We would say something like, we found a z equal to 2.25, and the p-value, or the alpha level, or the level of significance, is less than 0.05. Okay, so again, we'll do plenty of practice with this shortly here. The alternative, p being greater than 0.05, means that we failed to reject the null hypothesis and did not find an effect. So I'll show you how we do this by hand, and then SPSS will kind of take the reins from us at a point here and do some more complicated number crunching for us. So let's go ahead and look at one more slide before we hop over to some examples. We're going to do this with z-scores first. We use z-scores for our last set of topics, and they're a good introduction to using the normal curve. So what we're going to do here is, instead of calculating z for a single score in a sample, we're going to calculate z comparing a sample to a population. So notice that this z formula is a little bit different than the last z formula that we saw. And then I have a list of assumptions that go along with z. So you might be thinking, hey, it's kind of ridiculous that we always assume we have a normal curve. In this case, we're also assuming that we have random sampling. We're assuming that all observations are independent of each other or do not influence each other. We're also assuming that variation is the same before and after, for the most part, or across our group. So it's kind of a lot to take in, but just what I really want you to take from this information here is to just take statistics with a grain of salt, okay? And that's what we're going to be talking about for the rest of the course, that even if we find something statistically significant, we're relying on many assumptions, all right? We're relying on a lot of assumptions. That's why repetition and larger sample sizes is absolutely crucial to understanding information. So we're just going to practice the process and see what it's all about. So let's do it. Let's go ahead and hop over to the whiteboard, and let's get an example of this going. Okay, so I'm going to need a couple slides here, and I'll be kind of hopping around. So that's the beauty of you being able to pause and kind of review things that I'm doing here. So I am going to write out here kind of a long-winded example, but just so we can start to get used to the verbiage that we'll be getting used to here. So I'll abbreviate a little bit, but here's our example. All right, so let's say that we have a neurologist, okay? So a neurologist is testing, all right, testing a drug. All right, they are testing a drug in 100 rats. They think it's going to impact reaction time. All right, so reaction time is a very widely used, I think we've done an example with reaction time before, but reaction time is very widely used in cognitive psychology. It's meant to indicate a few things, but it's really meant to indicate things like attention span and quickness or strength of connections in the brain. So this is a pretty commonly used psychological variable here. So we're going to test a drug in 100 rats. So this is our sample. Okay, we're going to test it in 100 rats. But reaction time, normally, all right, so reaction time in rats is normally distributed, all right? We're going to call it normally, right? Normally distributed. And it is 1.25 seconds to react to a stimuli. So a stimuli could be something like flashing a light. As soon as the light flashes, if a rat presses a button, they get a treat. All right, this is kind of a behaviorist type of study. So let's say that this is what we know. So this is going to be something that we call our population mean. I'll go ahead and put this mu in here. Remember our Greek letter mu. So rats normally react, right, at 1.25 seconds with a standard deviation of, let's call it 0.5. Okay, and population standard deviation is going to use this nifty little sigma. This is lowercase sigma. Again, we've kind of brushed on these topics up until now, but here is where they are applied, all right? So we're going to take our sample of 100 rats and compare them to these known population values. And we'll talk all about how, of course, they've not measured every single rat in the world to get this value, but this might be the result of, say, a sampling distribution where there are lots and lots and lots and lots of samples that point to the direction that this is a normal reaction time and that it's normally distributed. So population starts to take on a little bit of a new meaning when we use it as a value in statistics. Okay, so with the drug, injection, mean reaction time is 1.05 seconds. So with the drug, okay, our sample of 100 have a reaction time of 1.05 seconds. Okay, 1.05 seconds. So what do we do here? All right, what do we think? So the first thing I'll mention here is that we're going to treat this as a two-tailed test, okay? We didn't say specifically that this drug was going to improve or reduce reaction time, but just that it was going to affect reaction time. So we're going to set this up as what we call a two-tailed test. And the first thing we're going to do is write out hypotheses. So I'm going to put down 4 steps here. So these are on the slides, but I'm going to start writing these out when we do examples to kind of keep us all together, keep us anchored in what we're doing here. So when you set up any hypothesis test, the first thing that you want to do is set up the hypotheses, all right? What is the prediction? The second thing that you want to do is establish the cutoff scores or the critical scores that will indicate what type of z-score we need to reject the null hypothesis. Third is calculating the statistic. In this case, we're calculating a z-statistic. Then the last thing we need to do is make a decision or decide what to do with our hypotheses. All right, so let's go ahead and start off simply, okay? So when we set up hypotheses, we do it like this, all right? We got our ho and our ha, our 2 new friends. And we're going to write them out. We're going to do 2 things. We're going to write them out verbally, and we're also going to write them out mathematically. So hypotheses are mathematical opposites. Null and alternative hypotheses are mathematical opposites, all right? So The null hypothesis is always no difference, no effect, no relationship, nothing happens. All right, so in this case, it would mean that the drug has no effect. All right, drug has no effect. And how do we write this out? So we have a sample that we want to compare back to our population. So this is where things conceptually get a little bit challenging, all right? So we're actually going to write our hypotheses out in terms of the population. So we're going to do something like, okay, the drug has no effect, then the population of rats who do take the drug will still be 1.25, all right? But now if the drug does have an effect, okay, so our alternative would be that the drug has an effect. So we need this hypothesis to be a mathematical opposite to our first hypothesis. So it would be something like, hey, our sample is not going to be the same or belong to this particular population, all right? So these are mathematical opposites. So mathematical opposites, okay? They are opposite to each other. If this is true, okay, this cannot be true. Only one of them can be true. So when we get to the end of this, when we do some math, one of two things are going to happen. We're either going to reject the null hypothesis, okay, or we're going to retain the null hypothesis. It gets to stick around, right? But that's going to be dependent on this information that we have up here, right? The population reaction time versus our new sample reaction time. So we're going to go ahead and worry about this soon here. But before we do that, let's go ahead and grab our cutoff scores for the z distribution. So let me go ahead and get a curve in here. Okay, so we're still working with the z distribution, all right? So I'll go ahead and put z over here to remind us. So remember that on a normal distribution for z, the center is 0, all right? And then we move in standard deviation units beyond this here. So what we're trying to do is we're going to calculate a z value, and we're going to see if it falls into the critical regions for this question. So let's see here. Are we going to test this? Let's test this at an alpha level. Let's get a new color here. And let me remind you, I will always give you the alpha level, so you're never going to have to make this up here. So this will be part of the question. I just don't like to crowd the whole whiteboard here with all this info here. But let's say that we're intending to test this at an alpha of 0.05. This is our most common alpha level. So this is a two-tailed test. Why is it two tails? It's two tails because there's no specific direction here. Maybe we predict that the drug is going to reduce reaction time. Then we would have something like a less than sign here. That's not what we're doing. When there's a does not equal sign, that means that this has two tails, and that we're going to look for critical regions in both directions on the normal curve, all right? So maybe we're going to significantly reduce reaction time, maybe we're going to significantly increase reaction time, right? No specific prediction was made. All right, so here we have it. Here's our normal curve. These are our critical regions. The areas I've shaded in the tails are our critical regions. All right, so alpha here, our alpha level of 0.05, remember this is a probability or a percent. In fact, it's 5%. So our shaded areas include 5% of the data under the curve. And since it's split into two tails, we have 2.5% of data over here, and we have 2.5% of data over here, right? So how do we figure out what marks this specific spot? Well, we might be able to go back to that trusty old z table that we used before, right? But we're going to use it in a slightly different way. Instead of, say, using it to find the distance between a z-score and any other given point on the curve, we're going to use it to figure out what percentage, right, or what z-score marks where there's 2.5% of data in the tail. So let's go ahead and hop over to the z-table and see how we can do this. All right, so remember that we have three different things reported here in columns, organized into two specific columns. So we have the mean to z and from z to the tail. So what we're looking to do here is find the area under the curve from a z value, which is currently not known, and the percentage in the tail, which we know is 2.5%. So if we follow the percentage and tail column all the way down to where there's only 2.5% of data in the tail, all right, we're getting closer, aren't we? Okay, let's see. We're looking for 2.5% of data in the tail. Keep on scrolling until we find it. Oh, I've gone too far. See the Z table? It just takes some patience, doesn't it? It just takes a little bit of getting used to. But what I'm looking at right now is I'm in the percentage in tail column on the very far right. Okay, so remember we're looking for a z-score, but we know that for our alpha level, we're looking for a z-score that marks 2.5% of data in the tail. So I'm following this percentage in tail column on the far right all the way down to where it says 2.50. Okay, there's a point where it says 2.50, and if we scoot over to the left, we'll see that the corresponding z-score is 1.96. 1.96. Let me go ahead and hop back over to the whiteboard, and I'm going to mark this, all right? So what this is telling us is that a z-score of 1.96 marks where there's only 2.5% of data in the remaining tail. So here we'll have a z-score of plus 1.96 and here negative 1.96. Remember, since we didn't predict a direction, it can go either way. Our calculated z-score could be negative, it could be all the way over here, or it can be positive and it'll be over here, all right? But regardless, for it to be a statistically significant difference between rats that took the drug and normal rats, we would need to find a z-score over here in these critical regions. All right, so I showed you how to find this on the z-table, but after this, we're actually going to do a little review in the z cutoffs that we will be using for the class. I mentioned before that we're only going to be testing at alpha levels of 0.05 and 0.01. So there's really only a handful of values that you will potentially need to know. So we'll go ahead and take a look at those in a minute here. But for now, knowing how to use the table is good. It's a safe bet. Okay, so look at us go. We have a lot of information here. So we have hypotheses set up, either the drug has no effect or the drug does have an effect. We have an alpha level. We've used the z-scores to determine the critical regions or the cutoff scores that we needed. All right, so we're done with step 1. We're done with step 2. We're going to calculate, all right, we're going to calculate a z-score and we're going to see where it falls. If it falls somewhere over here, right, maybe we get a z-score of negative 0.5. Maybe we get one of positive 1. Those are not in the critical region. All right, those do not fall in our critical region. So if we found any z-scores over here, that would be evidence to suggest our null hypothesis is true. If we find something over here, right, maybe we find a z that's equal to 3.5, all right, that would suggest that our null hypothesis is not true, right? That our group of rats that took the drug is inherently different from the normal population that we have this assumption about. All right, another way I like to think about this is that the null hypothesis is innocent until proven guilty, all right? So if we find a score that supports the null hypothesis, it's still innocent, right? We haven't proven it guilty. We don't prove it guilty unless we find a score over in our critical regions. So now that we're done with our first 2 steps here, let's go ahead and calculate a z-score. All right, let's calculate a z-score. I'm going to get us a fresh slide here to calculate the z-score. So we have a slightly new z formula here, though it's very similar to what we've been doing. But instead of comparing a single score to a sample mean, we're comparing a sample mean to a population mean. All right, so it's a little different. And instead of just dividing by standard deviation, we divide by the standard deviation of the population all over the square root of n. This particular figure here is something that we call standard error. This is a pretty commonly used term in statistics, and in fact, we'll use it again in the future. But this is our formula. All right, so we're going to calculate what we call a test statistic using sample data. Then we're going to compare that statistic to our critical regions that we placed onto our normal curve using the z-table. So let's go ahead and remind us of what our values were, all right? So X bar for the rats that did receive the drug was 1.05. All right, the mean of normally distributed rats reaction time was 1.25. These are both in seconds. We have a standard deviation here of the population of 0.5. And then we have an n equal to 100. Okay, those were all given in the question. And of course, when you have questions like this on the homework and on a quiz, they will be very flushed out, right? It won't just be my quick notes here on the whiteboard. So just make sure that you're taking note and practicing on those assignments to make sure that we're able to pull this information out of the question. So let's go ahead and plug this into the formula here, all right? So we have our X bar, all right, of 1.05. We are subtracting 1.25. We're putting it all over 0.5 over the square root of 100. Okay, so as always, I suggest that you check your math here, all right, along with me. But we have something like negative 0.20 up top, all right, and then this, of course, turns into 10, the square root of 100. 0.5 over 10 is going to turn this into a 0.05. And then this is going to give us a z-score. All right, let me go ahead and get us a different color here. But it's going to give us a z-score, all right, a z-score of -4, okay, a z-score of -4. So remember we learned that z-scores beyond -3 and +3 are pretty big, pretty uncommon. All right, so immediately you should start to think, hey, this is a big Z, right? This is a big Z-score. This particular sample is very deviant from the population mean. That's maybe what we should think. All right, so remember this isn't exactly the same as using Z-scores before, all right? Z is not going to be an exact direct reflection of our standard deviation units around the mean because we're combining both information from the sample and the population, but no less. What we want to do is take this -4 value and pop back over here to our curve. Is -4 in one of our critical regions? Okay, we did calculate. Let's get back to our other color. Is it in our critical region? Well, I think so, right? I would think yes. All right, it's somewhere over here, okay? A z of -4, all right? Z of -4 is in fact over here in this critical region. So let's think of it this way, okay? If we find a z-score that falls in these boundaries, okay, and this is 95% of the data, right? Because only 5% is in the tails. If we find anything over here, that would be evidence to support our null hypothesis. If we find anything over here, all right, here's our z of -4, that's evidence to reject the null hypothesis, all right? So we calculated, and now it's time to decide. We need to make a decision. All right, and what is the decision? Well, remember we're talking about unlikeliness, right? A z of -4 was very unlikely to happen due to chance. It seems like the drug that was given to these 100 rats changed their reaction time. And not just changed it, but changed it in a statistically significant way, right? Because it was very unlikely to happen given what we knew about the population. All right, so if we find a z statistic in the critical region here, we reject the null hypothesis. And here's another way I like to think about this, okay? So remember, this is a probability, this 2.5%. That's very low, right? Only 2.5% of the normally distributed data of the null hypothesis exists over here. So finding a z of -4, the probability of that was very low. We might say something like the p, right? P for probability is low, okay? So when the p is low, when we find ourselves over here in this critical region that was unlikely to happen, when the p is low, the ho, okay, has to go. Ho's got to go. We would reject, all right, we're on to step 4 here. We're rejecting the null, all right? Why are we rejecting the null? Because what we found was very unlikely to happen if the null were true. And it suggests that the null is not true for our sample, right? We're comparing to a population of our sample. our sample doesn't seem to fit in with the population because it seems that this drug has changed the reaction time of these rats. So notice my verbiage here when I'm talking about this. We don't say that we prove, right? We didn't prove that the drug reduced reaction times. And again, reduced reaction times is a good thing. That means they were reacting faster. So we're not saying we proved anything. We reject the null, but we don't accept the alternative hypothesis. All right, the way we would talk about this is we would say we rejected the null hypothesis. There is some evidence to suggest that the alternative hypothesis is true. Right? We're not saying that it is, but we're saying we have evidence to suggest it. And of course, what we would want to do after this is repeat the study, right? Repetition, this is back to the scientific method. We would want to repeat the study. We'd want to do it in larger samples. We'd want to do it in different samples. We'd want to make sure our sample is representative of the population of rats that we're trying to make a statement about. But there we have it. That's our first run through a hypothesis test. All right, so we did our 4 steps. We set up the ho and the ha. We established our cutoff scores. We calculated the z, right on our other slide here. We calculated the z, and then we made a decision about the z based on those cutoff scores. All right, so before we move forward with any more examples here, I do want to show you the main z cutoff scores that we'll be using and show you how you can find them using the table, because this will save you a bit of time when we're specifically working with z-scores. So I'm going to call these our z cutoffs, okay, our z cutoffs for hypothesis testing here. So we have different cutoff scores for two-tailed tests. All right, so I'll have 2 tails over here, and we'll do 1 tail over here. So remember, the tails are referring to if we have a direction of the prediction. If there's no direction, if we're just predicting a difference, we have 2 tails. All right. If we are predicting a difference, a specific difference, an increase, a decrease, maybe we wanted to predict that that drug was going to increase reaction times, right? That would be a directional prediction. That means that we're only looking in 1 tail. So here we have our 2-tailed examples. All right, let me go ahead and try and color this in nicely here. Keep us nice and organized. Okay, here we go. And then we have some 1-tailed test over here. So this is just like our normal curve table before, in that I'll be showing these to you on one side, but because this is a symmetrical curve, it can just be flopped over to the other side and a negative sign can be put on it, all right? So I'll go ahead and put them both over here. Okay, so we'll take a look at these. We'll do an alpha of 0.05 up top here, and an alpha of 0.01 on the bottom here. So remember, I'm only going to have you using alpha of 0.01 and 0.05. There are other alpha values, but these are the most common. If anything, we go with more restrictive or conservative values when we're doing research reports, but these will be just fine for our purposes here. So we can have these 2 different alpha levels, and we can have 1 or 2-tailed tests. So there are 4 different options that we can use for our cutoff scores. So I just want to bring these to your attention because you can either, jot these down, commit them to memory, but it'll save you some time using the z table to find these cutoffs, but I'll show you how we do this. So this is what we just did. We just did a 2-tailed test at an alpha of 0.05. So what we were basically saying here is that these shaded regions have 2.5% of the possible data in the null distribution. All right, 2.5%, or of course, if we're using the half of this, right, if we're having this particular alpha value, it'd be something like 0.025, right? We're just splitting it into 2 tails because we're interested in the 5% of the most extreme scores here. So we looked this up in the table, all right, so here's z, all right, so we know that the center of the z distribution is 0, and we had looked this score up, and I'll go ahead and pop back over to the z table here. So we're looking in the percentage and tail column on the far right, and if we scroll all the way down to where 2.5% of the data is in the tail, we find the z-score of 1.96, all right, 1.96. So let me go ahead and get a distinct color for these here. So 1.96, all right? This is what we would have to exceed for our z-value to be statistically significant in this scenario. But now let's go ahead and try for the 0.01 for our two-tailed hypotheses. So if we turn our 0.01 into a percentage, that's 1% of the data. But if we're splitting it across two tails, this leaves a mere 0.5%, right? Only 0.5% of the data is in here. And of course, my curves here are not drawn to scale, so please pardon that. But again, if we take 0.01 and we split it in half across these two tails, we get something like this, right? This is what we're doing. We're just using the assumptions that are true of a normal distribution to help kind of anchor our decisions here. So if we hop back over to the z table, all right, and we scroll to where the percentage and tail is just 0.5%. All right, so I'm looking in the percentage and tail column, all right, percentage and tail, and we're gonna go look for where there's just 0.5% in the tail. All right, so tragically here, okay, let's see what we got here. We have 0.51 and 0.49. We see that here, there's no clean 0.50. That's okay. You can use either of these values, all right? I usually use 2.57, but you might see me jumping between them. But that's how we find the cutoff here, right? We're looking for a z-score that indicates where only 0.5% of the data is in the tail. All right, so hopping back over to the whiteboard here, let's go ahead and mark that here in our nice bright red, something like negative 2.57 and positive 2.57. All right, that's the z-score we would need to surpass to be statistically significant at an alpha of 0.01 for a two-tailed test. So now let's try out the same thing here for one tail. So say we're predicting one specific direction, okay? So we're doing this quite often, right? Maybe more sleep leads to better mood, okay? That would be a directional hypothesis in which we're predicting specifically an improvement, right? If we change one thing, we're going to see an improvement. So what we have here is 5% of the data in one tail. We're not splitting it across two tails here. It's all going to be in one tail. It's easier, right, just probabilistically, to support a one-tailed hypothesis because you need a less strong test statistic in order to do so. So let's go ahead and see what we mean here. If we go back to the table and we go to where there is 5% of the data in the tail, all right, we have another case of, there's no exact 5, but we have 5.05 and 4.95. So again, I'm looking in the percentage and tail column. We find something like 1.64. 1.64 or 1.65, again, use whichever one you would like. But I'm going to go ahead and use 1.64 here. Okay. Then I'm going to put that, of course, we could, or negative 1.64. All right, so depending on the direction of your hypothesis, if you're predicting a decrease in something, we'd be using the negative value rather than the positive value. And then lastly, let's do the same thing here for a one-tailed hypothesis at an alpha of 0.01. So that means that we're expecting only 1%, okay, 1% of data over here, a 1% chance that we would come over here randomly. So again, probability still works in the same way, but we're just using it in a kind of different facet here. So let's go back to the table. We're going to go to where there is 1%, all right, 1% of data in the tail. Again, I'm looking in the percentage and tail column. We're going to where there is 1%, and again, we're stuck between 1.02 and 0.99. So just pick whichever of these two values. It will not make a difference to our final decision. So I'm going to use 2.33. All right, so let's stick with our red here. All right, so 2.33, of course, or negative 2.33 if we're looking in the other direction. So let this just serve as a reference to you. Again, you can always look these up on the z-table. It's not that you need to memorize these, but we're only going to be dealing with these 4 possibilities. So it's good to have these numbers in mind when we go ahead and do further examples. So with that, let me go ahead and give an additional example here. All right, let's try out just another situation, another circumstance here. And let's get a different color. Okay, so this has to do with behaviorists, okay? So a behaviorist, all right, a type of psychologist that's focused on behavior. So let's say that a behaviorist is interested in a new diet for their rats, okay? We're sticking with rats. So in a new diet for their rats. All right, so they are predicting, let's see, they're predicting a change. That's not how we spell predicting. Predicting a change in weight. Okay, so I'll go ahead and stop us here for a minute. All right, so predicting a change. All right, not an increase, not a decrease, a change. So that should be our first giveaway that this is a two-tailed test. All right, so this is the type of verbiage that we would look for in questions in order to determine if this is a one or a two-tailed test. All right, so let's see what we got here. Predicting a change due to change in appetite. All right, so something is known about the population. All right, so I'm just going to go ahead and write down some population statistics. And before I do that, I'm going to write down our 4 steps of hypothesis testing, okay? Because one of these we can do before we even have the data, all right? And in fact, hypotheses are generally created before we have data. It's a prediction, then we go collect some data and then make a decision about it. So here we have it. Let's go ahead and write our hypotheses first, all right? I think that's a good idea. Let's do our hypotheses first. I'll go ahead and put it down here. I'll mark it with a 1 here so we know that we're on the first step. All right, so our null and alternative hypotheses. So the null isn't very exciting. It's about the same every single time. So in this case, it would be that the diet has no effect. All right, and we'll do the mathematic hypothesis once we have the values here. But then the alternative would be that the diet has an effect. All right, so there's more than one way to write this, right? But we want to get this idea across, that a null hypothesis says that there's no effect, no difference, no change, whatever it is, and then the alternative is that there is some difference or change. All right, so let's go ahead and get some values in here for us to start thinking about. So let's say that this particular scientist knows that the population weight for the rats that they use is equal to 18 grams, all right, with a standard deviation of 4 grams. All right, so this is known about the population, or at least assumed about the population. Remember, we did a lot of talk about how it's very unlikely that we have every data point for an entire population, but we often make assumptions, right, to compare to, or what we believe to be true about a population given data that we have. So then we grab a sample and we compare to that. So let's say that our sample mean, all right, sample mean of rats with the new diet, they weigh now 15 grams, and we took a sample of, let's call the N 16, all right, 16. Now let's say that we want to test this at an alpha of 0.05. So remember, you're not going to have to determine alpha. It'll just be given to you. But this is the most common, 0.05 and 0.01. So this is what we will use. Okay, so this is what's given to you in the question. You'll have to come up with the hypotheses yourself. So that is our first step. So let's go ahead and try the next step. Let's see if we can establish some cutoff scores for this particular question here. Okay, so for 2, let's go ahead and get a curve going here. Okay, so we know that 0 is in the middle, right, for z. Since this is just predicting a change, all right, not an increase or a decrease, we know that this is 2 tails. And in fact, we can finish off our hypotheses now. All right, so remember that we're ultimately making a prediction about if our sample fits into the population, okay? So does our sample fit into this population, right, where the rats equal 18 grams, or do we belong to an entirely different group where the rats do not weigh 18 grams? All right. So if we're talking about this particular data distribution, and we're using the Z distribution here, if we're talking about the X distribution, which in this case is our sample or rat weight, we know that the mean for the population is 18. So this is us using the normal curve to represent the null hypothesis, right? So if the null hypothesis is true, we'll probably get a z-score that's very close to 0, and that will support our null hypothesis. Or if not, let me go ahead and get rid of some of this here. If not, we'll find ourselves out in these kind of no man's lands, right? Our critical regions. Right? If we find something out here in the critical region, something different is going on, right? It seems that the diet does have an effect because it's pushing us away from the distribution of the population. Okay, so how do we figure this out? All right, how do we figure out our cutoff scores? So we finished the first step and now we're on to our cutoff scores. We're using an alpha level of 0.05. So remember, when we were splitting into two tails, that means we have 2.5%, all right, of data in each of these tails. So we're using that same cutoff value, 1.96, a value that we might kind of start to get used to here. So if we surpass negative 1.96 in magnitude or positive 1.96 in magnitude, that means that our sample of rats is significantly different from the population. All right, so let's go ahead then and calculate, right? We have all of our values here that we need to calculate. And in fact, I think I might be able to keep it all on the same slide here. So let's give it a try. All right, so Z is equal to, all right, our sample mean, which is 15 grams, minus our population mean, which is 18 grams, all over the standard deviation of the population over the square root of our little n, all right, our little n of 16. Okay, so what do we get here? We have a difference of -3 up top, and then 4 over, the square root of 16 is 4 over 1, so we have a z-score of -3. -3. All right, so where does -3 fall? Does it fall over here by the null hypothesis, or does it fall in one of our critical regions? I think it falls into one of our critical regions, right? -3 is greater in magnitude than -1.96. So the probability of this happening was low. In fact, it was less than 5% likely, as evidenced by our alpha level. So remember, when the P is low, the HO has to go, right? HO's got to go. So that's our decision, right? We have to reject the null, right? We reject the null. So what does that mean? It means that the diet seems to have an effect, right? And specifically, it seems to have an effect in reducing weight gain of these rats, right? These rats seem to be of a significantly lower rate than the others, okay? So let's try, while we're still on this particular topic here, let's try some new examples, right? So let's say that this is just one sample, okay? This 15 grams is one sample, but let's say that you grab a few more samples. Let's say in one sample you get a mean of 17 grams, and in another sample you get a mean of, say, 19 grams. Well, we can go ahead and calculate Z for these as well. It's going to look the same. Everything here will be the same except for this particular value. So we know that they're all going to go over 1. So let's go ahead and try this out. If we do 17 minus the mean of 18 over 1, what do we get? If we take 19 minus the population mean of 18 over 1, what do we get? Well, we get a Z of -1 and a Z of +1. Where would these fall on our distribution? If we go back over here, right, -1 is not in our critical region and +1 is not in our critical region either. So if either of these were to be the sample we were testing, we would come to a different conclusion, right? This would mean that we would retain the null hypothesis, right? It seems that the diet doesn't have a significant effect on the weight of these rats. All right. So hopefully we're getting the hang of it. Hopefully we're feeling a little more comfortable with this now. This procedure, too, these 4 steps that we use in hypothesis testing are going to persist across different types of statistics that we use. So let's go ahead and try a few other examples or other scenarios here. So this one is about an ADHD drug, all right? So ADHD being attention deficit hyperactivity disorder. All right, so we use drugs to treat ADHD. So let's say that we have an ADHD drug meant to increase, okay? This is a big key word, okay? Meant to increase. This means we have a direction to our hypothesis. Let's say that it's meaning to increase attention span, all right? So let's say that we have some population values, okay, for those with ADHD. So the population mean, we'll go ahead and call it attention span for short. All right, population mean attention span score for those with ADHD is 50 on a scale, right? We have lots of scales that we use to measure different things in psychology. We have scales meant to measure attention span. So let's say that the mean of the population is 50 and the standard deviation, all right, so this is mu. And then the standard deviation is, let's call it 10, all right? So that's what's known about the population. So let's say that we're trying out this new drug on a sample of how many? Let's say we're doing for 400, okay, 400. And let's say that they score 51. Okay, wow, that might seem a little disappointing at first glance, right? 51, that's only a 1-point difference, a 1-point increase, all right? But let's go ahead and test it anyway, right? Let's say that we want to test this at an alpha of 0.05, right? We'll go ahead and keep it at 0.05, but remember, now that we have a direction, this is going to change how we make our final decision because we're only going to be looking in one direction, either above or below the mean. So let me go ahead and get our 4 hypothesis testing steps in here. I just like to have these around because it just helps to kind of remember what you're doing. It's a little bit of a long process, but it's a simple process. It's the same almost every time. So let's go ahead and get our information in here too, the population information and the sample information. Okay, so what do we know about the population? We know the mean is equal to 50. We know that the standard deviation is equal to 10. What do we know about the sample? They got an average of 51 with an n equal to 400. All right, so let's go ahead and start with our null and alternative hypotheses yet again. All right, how do we write these out? Okay, so for number 1, we need our null and alternative hypotheses. So the null hypothesis, hopefully we're catching on to this a bit, but this just means that the drug has no effect, all right? So that's exactly what I'm going to write. Drug has no effect. And that our sample is just going to fit into the population, okay? So the population of people who take this drug will end up just being equal to 50, okay? But now we want to test, say, to see if the drug has a positive, okay? And remember, there are more than one way that we can write these types of hypotheses out, right? We could say that the drug is going to increase attention span, but we'll say that the drug has a positive effect. And these are, of course, both related to attention span. So the drug has no effect on attention span. And then the mathematical hypothesis would be something like this. It would be that the score is going to be greater, right? It's going to increase the normal attention span score that we would expect from people with ADHD. All right, so let's go ahead and get a new slide here, and let's work on our cutoff scores. All right. Okay, so we did number 1, now we need to do number 2. We want to find our cutoff scores, so let's go ahead and get a curve here. All right, so since we're still working with the z distribution, the middle is going to be 0 when we're talking about z. In fact, I'll put it down here We'll keep the z-values down here, and if we're talking about the x metric, then we're talking that the mean is going to be 50. Right, that the mean is going to be 50. And what we're going to do is compare our specific sample to this and see if we fit into this distribution. So using those z values that I gave before, let's take a little journey back here. All right, this is a one-tailed test, all right? And a dead giveaway for a one-tailed test, pardon my hopping around here, is this, is a greater than or a less than sign in our hypotheses, and a term like increase or decrease in the question. Okay, so that's the giveaway for this being one-tailed. So if this is one-tailed and at an alpha of 0.05, we know what value we need to use, right? We need to use this value here. And since we're looking for an increase, we will be looking in the positive direction. So 1.64. Okay, so there we have it. And of course we could go to the z-table, right? Because if we're looking over here, all right, at an alpha equal to 0.05, we're looking for where 5% of the data is here, looking for that z-score. So if we hop back over to the table and we scroll to where there's 5% of the data in the tail, we'll find 1.64 and 1.65 here using that percentage in tail column. All right, so hopping back to the whiteboard here. Let's see, I lost my own whiteboard on my screen here. Okay, so here we are. Okay, so we know what we need to exceed in order for there to be a perceived significant difference between our sample and the population. So let's go ahead and do our calculation here, all right? Step 3. All right, so remember our z formula looks something like this. We're taking a sample mean minus a population mean, putting it all over the population standard deviation, and then dividing by the square root of n. So if we plug in our values, our group of those who took the ADHD drug had a sample mean of 51. If we subtract the population mean of 50 and put it all over our standard deviation of 10 over the square root of 400. Remember, we have a big sample this time. Let's carry on with this math. We have a difference of 1 point up top, so we might not expect to see much of a difference. And then we have 10 over the square root of 400, which is 20. So we end up with 1 over 0.5. Okay, and then this gives us a z-score of positive 2. All right, well, let's go ahead and put this onto our curve here, right? Where is plus 2? Is it in the critical region? I think so, right? So what does that mean? It means that this was very unlikely to occur if the null hypothesis was true. All right, so if we go back to our hypotheses here, or our hypotheses down here, we would reject the null, all right? The p, the probability of this happening was very low, less than 5%. So when the p is low, okay, the hoe has to go. All right, and that's just a fun way of saying that we reject the null. So we come back over here, we would reject the null, and we would say that we have some evidence, okay? We have some evidence for this. We have some evidence that the drug has a positive effect, even though there was only a 1 point difference. That's why variability is so very important, right? We have to include it in our calculations. So we would have evidence to suggest that this is true. All right. Let's try just one more, okay? Just one more. And then in a separate topic or kind of part 2 of this topic, we'll talk about a few more hypothesis testing considerations, but let's go ahead and try one more example here. Okay, so this is about your coolness, how cool you are, right? Because I know we're all very worried about that, as every young adult is. But let's say that you are interested, okay? You are interested in becoming cooler. Okay, cooler. I'm gonna underline the word cooler because we're trying to increase our coolness. All right, we're trying to become cooler, increase our coolness. This is a one-tailed hypothesis. All right, so you ask, let's say you ask all of your friends. okay? Everyone that knows you how cool you are. So you ask everyone, okay? AKA the population, right? You ask everyone that knows you how cool you are on a scale, right? A scale of 150. So you score a coolness score of 100, okay? 100. Let's also say with a standard deviation equal to 15. So in order to increase your coolness, what you're going to do is you start to wear sunglasses. You start to wear sunglasses all the time. Indoors, outdoors, at night, like cool people do, right? Okay, so you start to wear sunglasses. And then after that, you ask a sample, okay, of 30 friends. Okay, so this is going to be your N. A sample of 30 friends to rate your coolness after that point. And at this point, your mean coolness score is 112, so you have increased it. But let's say that you're not just interested in knowing if you've increased it. You want to know if you increased your coolness significantly. And this is not a joke to you. This is very serious. So you're going to test at a more conservative alpha level of 0.01. All right, you are serious about becoming cooler. All right, so let's go ahead and test this. We can test this in the very same way. So we'll set up our null and alternative hypotheses. We'll set up cutoff scores. Whoa, an extra F on cutoff. Okay, then we'll calculate, and then we will decide, did you get significantly cooler from this? All right, so let's go ahead and start with our hypotheses again. Let's get our two hypotheses here to just kind of anchor us. So let's just write them out verbally first, and then once we write out the data, we'll put the mathematical hypothesis in here. So the null would just be that the sunglasses have no effect on coolness, okay? They have no effect. Right, and then the mathematical would just be that you're just as cool as you were, all right? So the sample of new friends that you ask is just going to fit right into this sample. There's going to be no real difference. But then what we'll go ahead and say is that the sunglasses do have an effect. That's the alternative hypothesis. We hope that they have an effect, right? Because we're desperately trying to get cooler. And specifically by getting cooler, we want to increase this score. We want it to be greater than 100. So we know that we did score better than 100, all right? That was given in the question here, but the question is it significant? So let's get our population information here. The average here is 100. The standard deviation is 15. And then for the sample, all right, for the sample, we had an X bar equal to 112 and an N of 30. Okay, you asked 30 people. All right, so let's get a new slide here, and let's go ahead and try for our cutoff scores. So this is a one-tailed test because we're trying to get cooler, right? Increase our coolness, so we're only looking in one direction. And the alpha was 0.01, all right? That was given in the question. So we're only interested in 1% of the data over here, okay? So remember, these curves are meant to represent the population, or the null hypothesis. So this is assuming that the null hypothesis is true. So again, if we hop back over to those z-scores that we considered as our cutoffs, we're doing a one-tailed test, all right, one tail, so we're over here at an alpha of 0.01. So this is the score we want to use. We want to use 2.33. And of course, we could hop over to the table, go to where there's 1% of data in the tail. I'll go ahead and scroll down to it, and you can see that we find 1.02 and 0.99. Right in that vicinity is represented by a z-score of 2.33. And even if this was negative, right, maybe we were trying to decrease our coolness, maybe we're too cool, we would use the same value, just the negative, right, and we'd be looking at the other side of the curve. So let's go ahead and hop back over to our slide here. So far away, all right, we've come so far. All right, so 2.33, that's the score we need to beat, all right, in order to have achieved statistical significance here, to have gotten significantly cooler. Okay, so let's go ahead and try to calculate here, all right? Remember, our formula is still the same. Sample minus population all over the standard deviation over the square root of our sample size. So our sample mean was 112 after we started wearing sunglasses. Before, we were at a coolness of 100. We have a standard deviation of 15 that we're going to put all over the square root of our sample size, which is 30. So we end up with something like 12 over our 15 over, what's the square root of 30? Anyone know that on the top of their head? Square root of 30 gives us something like 5.48. If we carry out our math here, we get a z-score that is, let's get a different color, positive 4.56. All right, wow, that's a pretty big z-score, isn't it? Right, remember z-scores generally range from -3 to +3. So if we go ahead and take a look at our critical region, does it fall in our critical region? I think most certainly, right? It's very comfortably in our critical region. So then what do? The probability of this was low, right? Well, not a very good circle. Probability of this was low, all right? The p is low. Ho has to go, right? It's got to go. We don't have evidence that it's true anymore, right? We're going to say that sunglasses have no effect on coolness, but then we start wearing sunglasses and we get this much cooler, right? We have some evidence that goes against that, right? The null doesn't seem to be true anymore. Instead, we have evidence for this. It seems that the sunglasses did make you cooler. They did have an effect. So the next part of this topic, which we'll go over next time, is that we can make errors, right? It's possible that the sample of people we asked just rated us higher than other people might. But for now, right, this is the statement we would make about this data, right? If we get new data, we might amend this particular statement. But this is the basics of hypothesis testing. These are the main steps that we need to follow. This is the procedure that we'll be doing, again, not just for this, not just for z-scores, but for the remainder of the class. Hypothesis testing is elegant in this way that it can be mapped onto really any statistic that we're interested in calculating. So, as always, please be in touch if you have any questions on this topic.